Friends, we continue the discussion with fundamentals of discrete probability in the second session of third chapter of our course in discrete mathematics. The conditional probability and Bayes theorem are introduced in this session. As an application of the theory, information and mutual information also are introduced. Introduction to discrete probability. Anxiety to know future is just common to all of us. Impatience is another common thing. What will be the immediate consequence of these two? The answer is very simple. One would try to guess the possible outputs much before the completion of any process. Is there any scientific support for your guess? Of course, the answer is yes. The entire probability theory comes for our help. There are many processes like tossing a coin, throwing a die, etc., in which there are only a finite number of possible outputs. If it is unable to predict the exact output before the completion of the process, then the process is called a random experiment. Each output of the random experiment is termed an outcome. The set of all possible outcomes is called the sample space. Any subset of the sample space is called an event. A collection of events is said to be exhaustive if their union is the sample space. Two events are said to be mutually exclusive or disjoint if their intersection is an empty set. For example, in the random experiment of throwing a die, the sample space is the set of elements 1, 2, 3, 4, 5, 6. The event of getting an odd number is the set of elements 1, 3, 5. The events of an odd number, a prime number, perfect squares and perfect number are exhaustive. These events are respectively set of elements 1, 3, 5, set of elements 2, 3, 5, set of elements 1, 4 and the singleton set, set 6. Their union is the sample space. The events of a prime number and perfect squares are mutually exclusive as there are no outcomes common in them. Events are actually sets, so all the set operations are applicable to them. Probability. The probability of an event is defined as probability equals number of outcomes in the event by number of outcomes in the sample space. For any event, the complement also is an event. Probability of complement equals 1 minus probability of the event. Example, in the random experiment of throwing a fair die, there are 6 outcomes in the sample space. In the event of prime numbers, which is the set of elements 2, 3, 5, there are 3 outcomes. Thus, the probability of getting a prime number when a fair die is thrown is 3 by 6 equals 1 by 2. Next example, in the random experiment of tossing 3 fair coins, the sample space is the set of triplets HHH, HHT, HTH, HTT, THH, THT, TTH, TTT consisting of 8 outcomes where H stands for a head and T for a tail. The probability of getting exactly one head is 3 since the set of triplets HTT, THT, TTH is the corresponding event. Next example, consider the random experiment of forming 3-digit numbers using the digits 0, 1, 3, 5 and 6. There are 4 into 5 into 5 equals 100 outcomes. The event of getting an odd number has 4 into 5 into 3 equals 60 outcomes and its probability is 60 by 100 equals 0.6. Next, consider the random experiment of tossing 2 fair dice. There are 36 outcomes in the sample space. The event of getting the sum of numbers on the dice as 8 or 11 consists of 7 outcomes which are pairs 2, 6, 3, 5, 4, 4, 5, 3, 6, 2, 5, 6 and 6, 5. So, its probability is 7 by 36. Next example, digital data received from a remote site might fill up 0 to 32 buffers. Let the sample space be S equals set of elements 0, 1, 2, etc. 32, where the sample I denotes that I of the buffers are full. It is given that P of I equals 1 by 56 factorial into 33 minus I. Let A denote the event that at most 16 buffers are full and B denote the event that an odd number of buffers are full. Then A equals set of elements 0, 1, 2, etc. 16. B equals set of elements 1, 3, 5, etc. 31. A intersection B equals set of elements 1, 3, 5, etc. 15. And P of A equals 1 by 56 factorial summation I ranging from 0 to 16, 33 minus I equals 425 by 56 factorial equals 0.758. P of B equals 1 by 56 factorial summation odd I ranging from 1 to 31, 33 minus I equals 272 by 56 factorial equals 0.485. P of A intersection B equals 1 by 56 factorial summation odd I ranging from 1 to 15, 33 minus I equals 200 by 56 factorial equals 0.357. The principle of inclusion and exclusion can be used to determine the number of outcomes in the union of events. The probability of the union could be obtained as P of A union B equals P of A plus P of B minus P of A intersection B. This is known as the addition theorem on probability. Example, consider the random selection of a number from the first 30 natural numbers. Take A as the event of getting a multiple of 2 and B as the event of getting a multiple of 5. Then we can write the following events and the corresponding probabilities. A equals set of elements 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. B equals set of elements 5, 10, 15, 20, 25, 30. And A intersection B equals set of elements 10, 20, 30. Also, P of A equals 15 by 30, P of B equals 6 by 30, P of A intersection B equals 3 by 30. Now, P of A plus P of B minus P of A intersection B equals 15 by 30 plus 6 by 30 minus 3 by 30 equals 18 by 30. Here, the event A union B equals set of elements 2, 4, 5, 6, 8, 10, 12, 14, 15, 16, 18, 20, 22, 24, 25, 26, 28, 30 and its probability is P of A union B equals 18 by 30. Thus, the addition theorem is verified. Conditional probability. The occurrence of certain events can make changes in the probability of other events. For instance, in a cricket match, the captain who had won the toss may opt batting first. But if there was rain in the previous night or a snowfall in the morning, instead he may opt fielding. So, the event that the captain opts batting first depends upon the event that there was rain or snowfall. These types of situations are studied in conditional probability. Conditional probability. The event A under the condition that another event B has already been happened is called the conditional event. It is denoted by A given B. The probability of such an event is called the conditional probability and is denoted by P of A given B. It is defined as P of A given B equals P of A intersection B by P of B. Example, consider the following data. In arts, there are 45 boys, 25 girls and the total is 70. In science, there are 65 boys, 35 girls and the total is 100. The total number of boys is 110, girls is 60 and the grand total is 170. Let A be the event that a student selected is a boy and B the event that a student selected studies a science subject. Then P of A equals 110 by 170, P of B equals 100 by 170, P of A intersection B equals 65 by 170. Here, the probability that a science student called is a boy will be the conditional probability P of A given B equals 65 by 170 by 100 by 170 equals 65 by 100. Independent events. If P of A given B equals P of A, then we say that A is independent of B. For independent events A and B, we have P of A intersection B equals P of A into P of B, which is used as the condition to check the independence of the events. It is easy to prove the following for two independent events A and B. A complement and B complement are independent events. A and B complement are independent events. A complement and B are independent events. Sometimes finding the probability of the complementary event will be simpler than that of the event. For this, we use the equality, the probability of an event equals 1 minus probability of the complementary event. Example, consider the case that power to a room comes from three different lines which are named as A, B and C. Let these lines be live in 80%, 90% and 95% of the cases. It is required to find the probability that there will be light in the room on certain night. Here, if A, B and C represent the events that there will be power in the lines and A complement, B complement and C complement respectively represent the complementary events, then P of A complement equals 0.2, P of B complement equals 0.1 and P of C complement equals 0.05. The required probability is that of the event A union B union C. It is the probability of the complement of A complement intersection B complement intersection C complement. Now, P of A complement intersection B complement intersection C complement equals P of A complement into P of B complement into P of C complement equals 0.2 into 0.1 into 0.05 equals 0.001. So, the required probability is 1 minus 0.001 equals 0.999 or 99.9%. Next example, consider A as the event of drawing a red card from a well shuffled pack of cards and B as the event of drawing a number card. It is clear that P of A equals 26 by 52 equals 1 by 2, P of B equals 36 by 52 equals 9 by 13, P of A intersection B equals 18 by 52 equals 9 by 26. Now, P of A into P of B equals 1 by 2 into 9 by 13 equals 9 by 26. Here, P of A intersection B equals P of A into P of B. So, A and B are independent events. Bayes theorem. Let E1, E2, etc. En be mutually exclusive and exhaustive events and let A be any event. Then, Bayes theorem states that P of Ei given A equals P of A given Ei into P of Ei by summation I ranging from 1 to n P of A given EI into P of EI equals P of A intersection EI by summation I ranging from 1 to n P of A intersection EI. The conditional probability and Bayes theorem have a variety of applications in many real-life situations. As an example, consider the following situation. Let there be 3 surgeons named A, B and C in a hospital who are available respectively on 2, 3 and 2 days a week. Any patient admitted in the hospital will be attended by one of them. The success rates, that is, the probability that a patient is recovered after treatment of these surgeons are respectively 0.8, 0.9 and 0.95. A patient is admitted in critical state for surgery and died after the treatment. We can find the probability that the patient was attended by the surgeon C. Let us denote the events that the surgeons attend a patient respectively as A, B and C. Let the event that a patient dies after treatment be denoted as D. Then from the given facts, it follows that P of A equals 2 by 7, P of B equals 3 by 7 and P of C equals 2 by 7. Also, P of D given A equals 1 minus 0.8 equals 0.2, P of D given B equals 1 minus 0.9 equals 0.1 and P of D given C equals 1 minus 0.95 equals 0.05. It is required to find P of C given D. Here, the events E1, E2 and E3 mentioned in Bayes theorem are respectively A, B and C. Also, D is the event mentioned as A in the theorem. So, P of C given D equals P of D given C into P of C by P of D given A into P of A plus P of D given B into P of B plus P of D given C into P of C equals 0.05 into 2 by 7 by 0.2 into 2 by 7 plus 0.1 into 3 by 7 plus 0.05 into 2 by 7 equals 1 by 8. Information and mutual information. Usually, messages or statements convey information. If a statement asserts the occurrence of an event which is very much likely to happen, we say that the statement contains only a small amount of information. On the other hand, if a statement asserts the occurrence of an event which is very rare, then we say that the statement contains a large amount of information. In other words, if an event is highly specific, its probability will be small and the amount of information will be larger. If the event is vaguely told, then its probability will be large and so the amount of information will be small. For example, the amount of information conveyed by the statement, "It is going to rain soon," when told in the months of July and March are widely different. In July, rain is very much likely to occur and so the amount of information is small, whereas in March, rain is not likely to occur and so the amount of information is large. If P is the probability of occurrence of an event, then the information contained in a statement asserting the occurrence of the event is minus log P equals log 1 by P. Here, the logarithm is taken with base as 2. Consider any event with probability P which is always a number less than or equal to 1. So, log P will be non-positive or minus log P will be a non-negative number. Moreover, when P is small, the amount of information will be large, and when P is large, the amount of information will be small. Suppose that we receive from the computer as output a binary digit which is either 0 or 1 with equal probability of occurrence. If it is told that the output is surely 1, then the amount of information received is minus log 1 by 2 equals 1. For the output 0 also, the same will be the amount of information. We may take the unit for the amount of information as a bit. Now, if we receive 32 binary digits from a computer as output, and if all the 2 raised to 32 possibilities are equally likely, then the information we receive is minus log 1 by 2 raised to 32 equals 32 bits. In the following example, it is shown how an information is processed from the given data. Consider the problem of examining the likelihood that there will be a 1-hour examination when the teacher is scheduled to go out of the town. Let S equals set of elements x1, x2, x3, x4 be the sample space where x1 is teacher is out of town and examination is given, x2 is teacher is out of town and examination is not given, x3 is teacher is in town and examination is given, x4 is teacher is in town and examination is not given. Let P of x1 equals 1 by 2, P of x2 equals 1 by 16, P of x3 equals 3 by 16 and P of x4 equals 1 by 4. Let A denote the event that an examination is given and B the event that the teacher is out of town. Note that P of A equals 1 by 2 plus 3 by 16 equals 11 by 16 and P of A given B equals 1 by 2 by 1 by 2 plus 1 by 16 equals 8 by 9. The information needed to determine that an examination will be given is minus log P of A equals minus log 11 by 16 equals minus log 11 plus log 16 equals minus 3.46 plus 4 equals 0.54 bits. And the information provided by the fact that the teacher is out of town on the fact that an examination will be given is I of AB equals minus log 11 by 16 plus log 8 by 9 equals minus log 11 plus log 16 plus log 8 minus log 9 equals minus 3.46 plus 4 plus 3 minus 3.17 equals 0.37 bits. Let C denote the event that the teacher is in town. Since P of A given C equals 3 by 16 by 3 by 16 plus 1 by 4 equals 3 by 7, we have I of AC equals minus log 11 by 16 plus log 3 by 7 equals minus log 11 plus log 16 plus log 3 minus log 7 equals minus 3.46 plus 4 plus 1.58 minus 2.81 equals minus 0.69 bits. The fact that the teacher is in town makes it less likely that an examination will be given. Consequently, the mutual information provided by the presence of the teacher on the occurrence of an examination is a negative quantity. Let us recall what we have seen so far. In this session, we introduced the probability theory and discussed some of its applications with a stress to conditional probability and Bayes theorem. As another application, the concept of information and mutual information was discussed. The following questions are provided for you to practice. First, what is the number of different outcomes when 4 fair dice are rolled? Next, a student randomly marks the answers true or false in an examination consisting of 10 questions. What is the probability that the answers are alternatively different? Next, when 4 boys and 2 girls are seated around a table, what is the probability that the 2 girls will not sit together? Next, when 3-digit numbers are formed using the digits 1, 2, 4, 5, 6 and 7, what is the probability that a number randomly selected is a multiple of 4? Next, let P be the probability that a man aged 60 will die within 1 year. If there are 10 such men, what is the probability that at least one will die within 1 year? The following books are recommended as reference. Elements of Discrete Mathematics by C.L. Liu, Tata McGraw-Hill Publishing Company, 2nd edition. Miller and Freund's Probability and Statistics for Engineers, 5th edition by Richard A. Johnson, Prentice Hall India Private Limited. Hope you have followed this session. We will continue our discussion with relations and functions in the next chapter. Till then, goodbye.